In my previous video, I introduced the concept of enthalpy. In the next few videos, we will look more in depth at how to calculate enthalpy and discuss what it means for chemical reactions to have positive or negative enthalpy. Today we're going to discuss how stoichiometry can be used to determine the heat absorbed or released in a chemical reaction, and I'm going to demonstrate this by showing some examples. So every reaction has what's called enthalpy of reaction. That is delta H of reaction and this is also known as the heat of reaction. And this value represents the amount of heat absorbed or released during that chemical reaction. And stoichiometry can be used to convert between grams or moles of the reaction components and convert between the grams of moles of reaction components and the energy that's absorbed or released. So the important information to gain from that is it's used to convert between amount of reactant or product and energy and it represents the amount of energy absorbed or released in that reaction. Okay, so let's do an example of a problem where we're using delta H of reaction. And as I said, we can use stoichiometry to figure out how much energy is absorbed or released during this reaction. So here's our practice problem. And you can go ahead and pause the video here if you would like to copy it down. Okay. So we have a propane gas tank in a home grill, and it contains 13.2 kilograms of propane, and the problem is asking you to calculate the heat in kilojoules associated with the complete combustion of all propane in the tank. And it tells us that the delta H of reaction equals negative 2,044 kilojoules. So let's start off with what are we trying to find? So it tells us right here, we're trying to calculate the heat in kilojoules associated with the complete combustion of all propane in the tank. So we're trying to find heat in units of kilojoules. Information we already know is we know that we have 13.2 grams of C3H8, and we know that our delta H of reaction equals negative 2,044 kilojoules. Now our strategy is going to be to use stoichiometry. So in order to use stoichiometry, there's actually some more information that we need, and that's going to be our balanced chemical reaction. So this is a combustion reaction. You should be able to write one of these based off of a problem. So I'm going to get us started. I'm going to leave it unbalanced so that you can have some practice balancing this chemical equation. So for the combustion of propane, which is C3H8 gas, you want to think, okay, what other reactant do we need in order to combust propane? The other reactant in a combustion reaction is oxygen. Remember, oxygen is diatomic, so that's going to be O2 in gas form. And the products of a combustion reaction are always going to be CO2 and H2O. And I'm putting H2O in the gas form here because, I mean, it's a combustion reaction, it's on fire, it's going to be really hot, so the water is going to turn into water vapor. So if you want to balance this reaction on your own, pause the video here. So the correct balancing of this equation is going to be a 1, 5, 3, and 4. So we know we're starting with 13.2 kilograms of C3H8. We always want to start with the value, whatever we're given. In this case, we are given the mass of propane. So we're going to start with 13.2 kilograms of C3H8. So kilograms isn't really useful to us, so we need to put that in the form of grams. So kilograms will go on the bottom, grams will go on the top. We know that there are 1,000 grams in 1 kilogram. And now that we're in grams, we can use the molar mass to get to moles. It doesn't give us the molar mass of propane, so we're going to need to find that. So for carbon, we know that carbon is 12.01 grams per mole, and there are 3 of them, which should give us 36.03 grams per mole. Hydrogen is 1.01 times 8 to give us 8.08 grams per mole. And the total should be 44.11 grams per mole, and that is going to be our molar mass of propane. So we know we want our grams to cancel, so grams has to go on the bottom, so that'll be 44.11 grams of C3H8 for every 1 mole of C3H8. Okay, so now we're in moles of C3H8. And this is the point where we can actually get to kilojoules. And we're going to do that by using this delta H of reaction value that was given. And something that we want to keep in mind is that we're always going to use, we want to use these coefficients. So the coefficient for C3H8 is 1. So for every 1 mole of C3H8, we are generating negative 2,044 kilojoules. Okay, so the unit that we were trying to get to was kilojoules. We ended up in kilojoules, so we can check to make sure all of our units cancel. So let's see. Kilograms cancels with kilograms, grams cancels with grams, moles cancels with moles. We ended up with kilojoules, and that is the unit that we were trying to solve for. So as long as we plug everything into our calculator correctly, and as long as we put the numbers in the right places, then we should be getting the right answer. So you can pause the video, plug that into your calculator, make sure you get see what you get for your answer. And the answer that you should get is negative 6.12 times 10 to the 5th kilojoules. And what this means is that this number of kilojoules is released, so notice it's a negative value, which means energy is released from the reaction. Meaning that it is exothermic. And that's the energy that is released when you burn 13.2 kilograms of propane. So that's how you use stoichiometry to figure out how much heat is absorbed or released during a chemical reaction.